All right, this lesson is on half-life. The half-life of a substance is the time it takes for the half of the substance to break down or convert to another substance using the process of decay. This can apply to many fields of study, including chemistry, pharmacy. Natural decay is modeled by the function below. So the n of t is the amount remaining. The n of 0 is the initial amount. E is our exponential base of approximately 2.72. K is the decay constant, and T is the time. This might look familiar to you. If I write it as A equals PE to the RT, very similar in format. A is the end amount, P is the principal, the initial amount, R is that interest rate, and T is the time. And this is our formula when we use compound interest. So here's our first example. The half-life for radioactive carbon-14, it takes 5,730 years for that substance to decay to half the amount. The question is, how much of a 10-gram sample of carbon-14 remains after 15,000 years? So 5,730 years is our time. 10 grams is our initial amount. So it'll be N naught. And we're going to hold off on the 15,000 for now. And step one is we want to find out the decay constant. So as an interest rate problem, that would be like finding the interest rate, the R. We want to find the decay constant, the K. So we're going to substitute it into our formula. So I'm just going to go ahead and write the formula down again. N of T equals N naught of E raised to the negative KT. Now we start to put everything in. Since our initial investment, in this case, the initial carbon-14 is 10 grams, and it's half life, so half the amount that'll be left after 5,730 years would be 5 grams. So our N of T would be 5, our N naught would be 10, E raised to the negative K, K is what we want to find, and then time that it takes for it to decrease to half the initial amount is 5,730 years. And what we're going to do is we're going to use this equation and solve for K. So to solve it, we first isolate the exponential, so we divide both sides by 10. And then we're going to reduce. So 5 divided by 10 is 0.5. E raised to the negative 5,730 K. Now we're going to go ahead and take the natural log of both sides. And why we take the natural log is our exponential is base E, and natural log and base E are inverses of each other. So since these are inverses of each other, we will just be left with negative 5,730 K on the right. We're using our inverse property. And then the left is still the same. Now we have a nice linear equation that we can isolate for K by dividing both sides by negative 5,730. Now the K is alone. So K is approximately, and what might show up in your graphing calculator or your scientific calculator is a scientific number that looks like this. 1.21 times 10 to the negative 4th power. What that represents as a decimal is you move it 4 places to the left, so 0.0000121. So that is our percentage as a decimal per 1 year for decreasing. Now it says, use the decay function to determine how much of the 10 grams of sample will be left after 15,000 years. So we're going to go ahead and write that function. So that initial amount was 10 grams E, and then we now substitute our K from up above into our formula. So negative 0.000121 K. So this is now our function for the problem. Now it's asking us to make a prediction. After 15,000 years, how much will be left? So this will be now our time in our formula. So we substitute 15,000 in for time, and then we enter this into the calculator. So after approximately 15,000 years, we'll be left with 1.63 grams of carbon-14 in that sample.